Hello everyone, I'm Pratyusha Das, a PhD candidate at University of Southern California, and today at ICASSP, my presentation topic is gradient-based class activation mapping for spatiotemporal graph convolutional network. So in my talk, first I'll talk about the motivation behind our work. Then I'll move on to the conventional gradient-based class activation map. And then I'll talk about spatiotemporal graph convolutional network and how we design the gradient-based class activation map for this spatiotemporal graph convolutional network. Then I'll move on to my experimental results, and then I'll conclude my work. These spatio-temporal graph convolutional networks gained a lot of popularity in the last decade, and they are very popular to understand any kind of spatio-temporal data, for example, traffic forecasting, activity recognition, etc. Because it captures the spatial correlation and temporal pattern in the data simultaneously, it can give you or it can extract very good, powerful features. But the problem is it lacks interpretability and the reason, and we don't know the reason behind their prediction. Now, gradient-based class activation map was first proposed to understand the outcome of the convolutional neural networks. CNN uses 2D spatial convolutional filters, and this GradCam detects the spatial image importance region to understand the prediction of the network. So, for example, given in this figure, if you look at the middle photo, if I want to understand if there is a dog or not, the network will look at this region of the image to predict if there is a dog or not. And if you look at the leftmost figure, if the network wants to understand if there is a cat or not, the network will look at this region of the image. Now we are trying to design a method which can understand the important region of the data, which is spatially and temporally important region of the data. Now, what is this spatiotemporal graph convolutional network? So after each layer of STGCN, we compute the output using this equation. So for a given graph, we have the adjacency matrix, and this A tilde is the normalized adjacency matrix. Q is the edge weight matrix. Xn is the spatiotemporal data, and W is the stack weight vector. Now, W and Q are the learning parameter here. And after each layer of STGCN, we compute the output using this equation. Now, given our input data, we pre-process the data and then apply multiple layer of STGCN block to compute the feature. And at the end, we apply a fully connected network along with a softmax to get the probabilities of each class, and then we predict the class. Now, for a given STGCN network, we are interested in learning what are these filters are basically learning. So from a CNN perspective, we know the last layer of CNN, and in this case, STGCN, basically captures the high-level optimal spatiotemporal information. But and these STGCN blocks, we will see in the later slide, that also retains the spatial and temporal localization of the data. Now, once in the output stage, we apply the fully connected layer, the localization is lost, but the neurons at this stage basically captures the class-specific information. So how the input data is contributing to the final decision. And for that, we are designing this GradCam method for STGCN. Now, for a spatiotemporal graph convolutional network, let's see how the filters work. So in this case, as a spatial filter, we are using the adjacency matrix, And what it is basically doing, it is taking the weighted average of the neighboring nodes for a particular node. And once the spatial filter is applied, we apply the temporal convolution on the temporal dimension of the data. And as our graph is pre-structured, this is a separable transformation. And here in this figure, what you are seeing that from L minus 1th layer to Lth layer, how we compute the feature. So for this particular node, we take a weighted average of their spatial node, at the same time the temporal nodes, and then we are the output is stored for the next layer, and so on. So as we can see, the spatiotemporal localization of the data is retained by the STGCN. Now, so now let's see how we can design the spatiotemporal graph GradCam to understand the output given by STGCN. So to create the joint time importance map, we use this equation. Now let's try to understand this equation. Here FKL is the kth filter at Lth layer kth feature map, and we take a weighted average of all these filters, and then we apply ReLU to get the joint time importance map. Now the question is, how can we design this weights? And one more thing, why we apply ReLU? ReLU considers the positive value which contributed to the final decision. That's why we apply ReLU on this weighted average to get the joint time importance map. Now, the question is how we design these weights. Weights are calculated based on the gradients. So given our Cth class score YC, we compute the gradient based on, at Lth layer, based on the kth feature nth node, or if for activity recognition task, nth joint, and tth time point. Once we get this gradient, we take an average over all time point or all frames and all nodes. And once we get that, we get the weight for that kth feature map. And once we compute the weights, we can do this weighted average to extract the joint importance map from based on our gradients and the feature map. Now, in this case, in our experimental setting, we considered a spatiotemporal graph convolutional network, which was used to understand the human motion. And in this case, particularly, they have used skeleton-based skeleton data to do this activity recognition task. In this skeleton data, there were 25 joints, and they made a spatial graph out of these 25 joints, and then they applied this STGCN. Now, in this STGCN network, this was proposed by Yan et al. And in this STGCN network, we have 10 layers or 10 blocks of STGCN. And this was trained on famous NTU RGB dataset. There were 60 classes, and the accuracy they can achieve was 81.5%. Now, what we are going to see as spatially and with time, how the importance of the joint is changing. Now, bigger the size of each node, you will see, is higher the importance of that particular node. And for a particular action, because of space or time, we couldn't show all the time point. Here, I'm just showing at the initial action, what was the joint importance map. In the middle frame of the action, what was the joint importance map, and at the end of the action, what was the joint importance map. So basically, you were seeing the joint importance map spatially and at the same time temporally. And as you can see that for an action throw, there's a higher activation on the right hand of the skeleton, which is obvious. And at the same time, as the end of the action, this portion, the hand portion, is much more active. That means the network is looking at this position or this particular node of the data to understand which action it is. Here is another example, kicking one person, and you can see how the spatio-temporally, the importance of the nodes are changing. Here is a sitting down action. Interestingly, at the end of the action, when the person sat down, there is no active region of the body. That means the network is not looking at this point of this frame of the data to predict that this is a sitting down action, and here's a standing up action, and you can see how the importance of different nodes are changing over time. Now here, there you are saying the spatio-temporal joint importance map, and to get a joint importance map for each of the action, what I did, I took the spatio-temporal joint importance map for all the data points and took an average over all the time points and all the data points in particular class to create these to create this joint importance map for the 60 actions. Now, the y-axis are the joints, and the black means it's not important, the white means it's very important, and this is the color scale. Now, the x-axis is the action classes, and how I arranged the actions is the first 47 or 48 actions are mostly the upper body action, and the rest of the action, which is marked in blue on the right side, is basically involves the full body action or the lower body action. And as you can see that when the upper body was more active, the network is also looking at that portion of or that area of the body to understand that this area is more this area is important, or this part of the data is more important to understand or predict this class. Now, we were interested in if we reduce the number of layers in the network, how the network behaves. And we randomly deleted 3 layers of the network and trained the network again. And we found that the accuracy dropped drastically to 60%. Now, the question is, why so? And when we applied GradCam to create this joint importance map for this network with 7 layers, we see that the network is basically looking at the upper body, upper region of upper part of the body, and specifically the hand portion of the body. And we have seen that in our data set also, it's a upper body heavy data point, means maximum actions or majority actions involves upper portion of the body. When the network is needs more layers or more complicated layers to understand all the actions, when we have a smaller network, it is basically looking at the upper portion of the body or to getting majority of the actions right. But still, the accuracy dropped to 60%, and this was a very interesting result. Now, how do we believe that what this STG GradCam is telling is right? Now, we can rank the body joints depending on the importance given by this STG GradCam. And once we rank them, we can mask the important nodes for a particular task and see how the accuracy is changing. So if we mask the important nodes, then the accuracy should drop drastically. If we mask the non-important nodes, then it shouldn't affect the network a lot. And that's what we have also witnessed in our results. So here XUB and XView is different train test protocol. XUB is cross person setting and XView is cross camera view setting for our training and testing. And when we mask the important nodes we see that for a smaller amount of masking, it is not affected. But when we masked it 50% to 90%, the accuracy dropped drastically. But when we mask the non-important node, even if we mask the data to 90%, it did not drop a lot. So that means what it is very faithful, or what STG Gradcom is actually saying, that this part of the data is important to predict this action is actually right. Now, to conclude my work, we designed a method to interpret the outcome of STGCN and the reason behind the decision made by STGCN. And it's a very generic method. If we just change the graph, we can implement it for any application, for traffic forecasting, and we can see that to predict traffic data for a particular area, let's say, which other areas are important, or which other areas of that neighborhood is important to predict or forecast the traffic for that particular area. And that's our next task, is to implement this method in different application, for example, traffic forecasting, and also to see the importance, joint time importance map at different layers of SDGCN. Thank you so much for your time. You can send me any question at this given email ID.